This is lesson 4.4, and in it we're going to solve two kinds of equations. We're going to solve exponential equations and we're going to solve log equations, and they each have a process that's very helpful described in this video for you to solve them. First of all, a definition. An exponential equation is an equation containing a variable in the exponent. So here is an example of an exponential equation. Here is an example. Here is an example. In this one, the base is 2. Here it's 4. Here it is 40. Some exponential equations can be solved by expressing each side of the equation as a power of the same base. That actually is a little rare to get that kind, and I'm not sure that we're going to have any in our exercise. If we do, I'll come back and I'll talk about this, but it is a rather unique way, and it only works if you have the same base or can express each side with the same base. Just as a quick example, if you had 2 to the x is equal to 8, because 8 can be written as 2 to a power, you could rewrite this as 2 to the x equals 8 is the same as 2 to the third. If 2 to the x is the same as 2 to the 3, then x must be 3. But it has to be, this condition must be met where both sides can use the same base. Just doesn't happen all that often. Instead, what we're going to do is we're going to isolate the exponential expression. We're going to take the common log on both sides of the equation for base 10. Take the natural logarithm on both sides for bases other than 10. And then we will use one of these properties, the natural log of a base to the x power. Remember, the power rule said the x could come out as a coefficient. If instead we have the ln of e to the x, we know that we get x. If we get to use common logs, in other words, if the base is 10 in the problem, then we get that the common log of 10 to the x is x. You'll see what I'm talking about as we look at each one of the examples, but it is this box and its information that I think you will want to write down. All right, let's look at number 1. In this problem, come on, slow down. The base is e, and it's e to the x is equal to 9.33. Now, in this one, because the base is e, I'm going to use ln. The base with its power is already isolated. So what I'm going to do is I'm going to take the natural log of both sides. I'm going to take the natural log of e to the x is equal to the natural log of 9.33. Now on the left-hand side, the base of a natural log is e. This base is e. That means that this, using those properties, simplifies to x is equal to the ln of 9.33. When I say those properties, they are the properties that I have circled here. They are from the previous lesson 4.3. So the first thing that my math lab wants is for you to write the solution set expressed in terms of logarithms. So you will literally type in ln, and it will open parentheses 9.33. All right. If it doesn't open parentheses, then you don't have to type the parentheses. The second thing is Now use a calculator to obtain a decimal approximation for the solution. So I'm going to go to my calculator. I'm going to go second quit. Now I'm on the home screen. I want the natural log of 9.33, close those parentheses. The instructions said 2 places, so let me get that again. And my answer, x, is approximately 2.23. So here it will be 2.23. For some reason my decimal point didn't want to stay. So I write this answer, it's in log form, and I write this answer, which is a decimal approximation. Remember, logarithms and exponentials are inverses of each other. If the base is e or any other number other than 10, we'll probably use natural logs. Well, in fact, they tell us to. It can be solved with a common log, but they've asked us to, so that's what we're going to do. All right, it says solve the following exponential equation. This one, the base is 7. All right, it is isolated. So I'm going to, I have 7 to the x is equal to 71. I'm going to take the natural log of 7 to the x is equal to the natural log of 71. I'm going to use the power rule that says the x can be moved in front. This becomes x ln of 7 is equal to ln of 71. I hope you remember your properties from the previous lesson. This one says if you have log base b of 7 to the, well, let me change that. Let's say it's y to the z power, that's equal to z log base b of y. That in our expanding rules that becomes the coefficient. Now to solve for x, I would divide by the natural log of 7, divide by the natural log of 7, x is equal to the natural log of 71 over the natural log of 7. All right, now they want me to write it in terms of logarithms. So we have ln 71 divided by ln of 7. Those parentheses may not be necessary in my math lab, but when I get my approximation, they will be important, so I go ahead and write them. It wants a decimal approximation, so I'll take the natural log of 71, close those parentheses, divided by the natural log of 7, close the parentheses, enter, round to 2 decimal places. This is 2.19. Let me go ahead and get that. Just in case you wonder what it looks like when you put it in the calculator. And this will be 2.19. So you're writing it in log terms, and then you're doing an approximation by using the calculator home screen. Let's look at number 3. Now the instructions, the steps, said to isolate the exponential term. Well, it's got a coefficient of 7. So to do this, I'm going to divide both sides by 7. So the first thing I'm going to do is take 3983 and divide it by 7. I don't know if it goes in evenly. It does. So I had 7 e to the 5x is equal to 3983. To isolate, I will divide both sides by 7. I get e to the 5x is equal to, let me see what that number was again. Whoops, let me close something that's trying to open. All right, it was 569. Now, because it's base e, I definitely want to use a natural log. Natural log of e to the 5x is equal to 569. Now, if you wanted to, you could use that power rule. You could say that the natural log of e to the 5x, that could go as the coefficient, it is 5x times the natural log of e, but the natural log of e is 1. 5x times 1 is 5x. But one of the properties takes advantage of that and says, because the base of the natural log is e, and this base is e, those are inverses, and you get 5x is 567. Divide by 5, divide by 5. Now this is not going to go in evenly. Oh, I'm so sorry. Hopefully you caught my mistake. I got so caught up in the left-hand side that I did not take the natural log of 569. I apologize for that. So it is the natural log of 569 divided by 5. X is the natural log of 569 all over 5. This is your first answer. Your second answer will be the approximation of that. So now I'll go to my calculator, and I have the natural log of 569, close, divided by regular old 5. Round it to 2 decimal places. I should get 1.27. And this is my second answer. So one of them I left in, let me move this again. One of them I left in terms of logarithms, the other one I put in the calculator. All right, let's look at number 4. It's a little more complicated, but once again, the base is e, which means I'm going to use natural logarithms. Now, before I can do this, I am supposed to isolate the exponential. So I have e to the 11x minus 3 minus a 7 is equal to 20,574. So I'm going to add 7 to both sides. That gives me e to the 11x minus 3 is equal to 20581. Now I'm going to take the natural log of both sides, so it's the natural log of e to the 11x minus 3 is equal to the natural log of 20,581. Using my inverse property, I know that the natural log, which is a log base e, of e to a power is equal to that power. 11x minus 3 is equal to the natural log of 20,581. I'm going to add 3 to both sides. Now, please understand you are not adding 3 to the argument of the logarithm, so I'm going to write it as 11x is equal to the natural log of 20581 in parentheses. That's the argument of the logarithm plus a plain old 3. Divide by 11, divide by 11, and x is equal to the natural log of 20,581 plus 3 all of that over 11. Now when I type that into my calculator, it will be the let me go back. I'm going to clear. This entire numerator I'm going to put in parentheses. Natural log 20,581 close plus 3 close for the whole numerator, and go back and get rid of an extra plus sign. All right, that's the numerator divided by 11. And I get 1.18 if I'm going to round it, and it says to round it. So let me move this. And it got tiny, and it seems to keep getting tinier. There seems, I'm going to do it again. All right, it was a little bit too difficult to get that to show, so this is what it is, and it's kind of messed up what I had written here. Certainly you could just rewind the video or go backwards just a little bit, and this is your expression. The entire numerator, because it had not only a logarithm but a plus 3, needed to be in parentheses and then divided by 11. Okay, let's move this out of the way, and I'm erasing something that you already have written down if you were writing. All right, now we're going to switch. Now I'm going to solve log equations. So think about how you solved exponentials. You took the log of both sides. You can do something similar with log equations, but I'm going to teach you something that is so much easier. We're going to express the equation in the form log base b of some m, where the x will be, is equal to a constant. Now, this works when there is only one logarithm, and if there is more than one logarithm, you might have to condense to combine them to have a single logarithm. But what we're going to do is we're going to rewrite our log statement as an exponential statement, and we did this, I believe, in lesson 4.2. We do need to check these because remember, logarithms have very restrictive domains. In this, the domain, you have to make sure that m, whatever is m, is greater than 0. All right, let's take a look at number 5. All right, we have log base 4 of x is equal to 2. Do you have a single logarithm statement? Yes. Then let's rewrite it in exponential form. The base is 4, the exponent is 2, and it is equal to the value, which is x. If you want to turn it around, x is equal to 4 squared, so x is equal to 16. Is that a domain violation? And remember, for the domain, whatever is here as the argument has to be greater than 0, and certainly 16 is greater than 0, so that is my answer. It will want 4 to the second, which is this statement, and it will want 16. All right, let's look at number 6. I have log base 2 of x is equal to 4. When I rewrite this in exponential form, the base is 2, The exponent is 4, and it is equal to x. Turn this around. X is equal to 2 to the 4th. X is equal to, well, it turns out 16. The problem was different, but I did happen to get the same answer, 16. I don't have to write that earlier version in number 6. But I believe I will need to do that in number 7. All right, I'm supposed to solve this. Okay. First of all, it says rewrite the given equation without logarithms. Do not solve. So this is just where I am rewriting it in exponential form. The base is e because it's a natural log. The power, logarithms are always equal to the exponent, and that's equal to x. So you could write it this way. I'll probably just write x is equal to e to the 8th. And I believe that you will find your e, let's see, you will find your e in the toolbar. Don't just pick e off the keyboard, I don't think. It should be in your tools. All right, the solution is, before I approximate it, it is e to the 8th. Remember, e is just a number. It's about 2.7. Now it wants a decimal approximation. So going to my calculator, I do second of the ln key is e to a power, the 8th power, and that gives us, and I lost it, gives us 2980.96. So 2980.96, because I'm still rounding to 2 decimal places. Okay. So we want to make sure the log is written as just a single logarithm, and then we will swap it to its exponential form and be able to solve. Let's look at number 8. Solve the equation. What is the exact solution? Select, okay. So the first thing we want to do is give the exact answer. Well, let's write this in exponential form because it's a natural logarithm. The base is e, the power is 6, and that's equal to x. These we're able to solve in one step. Not all of our problems will be quite this easy. All right, so the solution set is e to the 6th. And then what is e to the 6th? Second of the ln key, 6th, enter. That's 403.43. 403.43. All right, number 9, a little more complicated, but that will make it just more fun. I have the log base 3 of the quantity x plus 2 is equal to 4. I do have a single log expression. I'm going to rewrite it as an exponential. The base is 3, it's raised to the 4th power, and it's equal to x plus 2. So I'm going to turn it around. X plus 2 is equal to 3 to the 4th. To solve for x, I would subtract 2 from both sides, and I get x is equal to, I have a mess, I'm so sorry. Subtracting 2, I'll get 3 to the 4th power minus a 2. This is my, let's see, the first thing it wanted me to do, you have to read the instructions because it kind of changes up per problem, is to write it in this format. So 3 to the 4th is equal to x plus 2. Then it wants, select the, okay, it wants this, it doesn't really, oh, it says, give the exact answer. Well, we can do this quite easily, actually. I was being slow with it. I'm actually going to raise 3 to the 4th power and subtract 2. So there's no approximating. So it's 3 raised to the 4th power. Get out of that. Minus a 2 gives me 79. All right, let's look at number 10. I have the log base 2 of the expression x plus 7 is equal to 3. So I have 2 to the 3rd power is equal to x plus 7. 8 is equal to x plus 7. X is equal to, subtract 7 from both sides, 1. And I'm sorry I haven't always been saying it, but I do in my mind think, oh, if I put 1 in there, 1 plus 7 is 8, that's greater than 0, so it works out just fine. Let's look at number 11. All right, now this has more than one log statement, so I need to remember that the sum of 2 logs is equal to the log of the product. I'm condensing. This will be log base 5 of x plus 8 times x plus 4, and that equals 1. So I condensed it. All right, now I'm going to rewrite it in exponential form. So I have 5 to the 1st power is equal to x plus 8 times x plus 4. In order to, let's see, it just wants me to give the answer. I don't give any intermediate answers. So 5 is equal to, 5 to the 1st is 5. Let's multiply these by FOIL. That's x squared plus 12x plus 32. Subtract 5 from both sides and get x squared plus 12x plus 27. That is factorable. If it were not factorable, I would use the quadratic formula. And I have x plus 9, x plus 3. So if x plus 9 is 0, x is negative 9. And if x plus 3 is 0, x is negative 3. Now, getting these negative answers is kind of making me think, am I going to violate the domain? Remember, when you plug a value in for x, it has to be greater than 0. If I put negative 9 in the place of x, this will be negative, and this will be negative. And what that means is I have to throw away that answer. If I put negative 3 in here, negative 3 plus 8 is 5. That's okay. Negative 3 plus 4 is 1. That's okay. I'm not going to do a full-blown check. I'm just checking for domain violations. So this is my only answer, negative 3. Number 12. I have a formula. So now I've got an application problem. It says A equals 24.2 e to the 0.0774 t. Models the population of a U.S. state A, so this is the population of some state, in millions t years after 2000. What was the population of the state in the year 2000? So part A, if the year is 2000, then t is 2000 minus 2000, which is 0. It is 0 years after 2000. So A is equal to 24.2 e to the 0.0774 times 0. Now I'm going to do this by hand, and then I'm going to turn around and do it in my calculator. So A, which is population, is 24.2. E to the product of those is 0. E to the 0 is 1. Multiply by 1 and it doesn't change it, so the answer is 24.2 million. If I had typed that into my calculator, into the y equals, because it is a formula, I would have typed in 24.2 second ln 0.0774. I'll use variable x. Now, if x is 0, second table, this is very tiny, but you can see that if x is 0, y is 24.2. So you could have done it with your calculator. All right. The next question, B, it says when, well, it doesn't. Now, there it is. It wants to know the population of the state will reach 31.4 million in the year. They're giving you A is 31.4. So we have A is equal to 24.2 e to the 0.0774 t, and the value of A in this example is 31.4 is equal to 24.2 e to the 0.0774 t. Let me get a little more space. All right, I'm going to isolate the exponential. So I'm going to divide by 24.2, divide by 24.2, and okay, I have 31.4 divided by 24.2. Well, that's a pretty messy number. Maybe I'll just leave it like this, and I will have e to the 0.0774 t is equal to 31.4 over 24.2. I'm going to take the natural logarithm of both sides. ln of 0.0774 t is equal to the ln of this fraction, 31.4 divided by 24.2. I'm taking a natural log of e. That's going to give me 0.0774 t is equal to this natural log, 31.4 divided by 24.2. And I'm going to divide by 0.0774. You can put the 0 in front if you want to. Divide by 0.0774. And I have t is this crazy looking answer, ln of 31.4 divided by 24.2 all over 0.0774. What in the world is that equal to? And then I'm going to show you a calculator way to do it. All right, the numerator is ln 31.4 divided by 24.2, all of that, divided by 0.0774. All right, this is t. So t is equal to 3 point, let me grab that back, 3.37. That's years, but it wants to know what would it be on the calendar. So it is 3 years after, 3 years and some months after 2000, so the year is 2003. All right, now having done all of that, let's go back because we haven't done this much. We still have in the y equals this. We have the function. Go to another y equals and put in the y value that they've given you, 31.4. Let's go to window. I'm going to go from -10 to x's or years. I'm going to put 50. And the y's, oh my goodness, these are in millions. So I'm going to put -10 to the 6th. And the max, that's a million, negative a million. And I'm going to put 50 million. Okay, I think my y values, oh my goodness, I was outrageous with my y's. My y's don't need to be that big. I don't need to set them in millions. I just get to use the word million. So -10 to 50, I apologize. There we go. There's that exponential curve. That is 31.4 million. Second intersect, number 5. And I toggled so that I am traveling along the horizontal line. Remember, when you're given a y looking for the x, you use the y equals and then intersect. 1, 2, 3. And there is there's my number, 3.365. I got it right here. That's 3 years after 2000, so it's 2003. Once you set the window, it's probably easier to use the calculator. I was not thinking about the fact that I had millions and all I had to do was say 31.4 and it was implied to be millions. All right. Let's look at our next question, all right, before I go any further with these application problems, I do want to remind you of something, and I probably should have done this before the last question. If you have a y equals blah 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 in your y equals screen, if you are given an x and asked to find a y, you use table, and it's really quite easy. But if you are given a y and asked to find the corresponding x, you have y1 and y2. You put that second y value that you're given down here. This is the given one. This is your formula or your function. And you do, the hard part is sometimes adjusting a window, and then you do second calc intersect. perhaps it would be worthwhile to make a little notation of that. All right, number 13, the function f of x is equal to 20 times 0.955 raised to the x models the percent of surface sunlight, which is your y value, that reaches a depth x feet below the surface of the ocean. And this is a picture of it. As you go deeper, less and less percentage of light filters down. Use this function to determine at what depth. Now, depth is x, so we need to find x when what? When there is 1% of surface light. When y equals 1. All right, so I'm going to go into my y equals and put y1 is equal to 20, open parentheses, 0.955 raised to the x power, and then y2, because I've been given a value of 1 for the 1%. All right, so I am probably looking for a value right about here. Let's go to our grapher. All right, the function, the formula is 20, open parentheses, 0.955, close, raised to the x power, and y2 is 1. All right, window. Certainly want to change this. The x's. Let's use these scales. The x's went from 0 to 65. So 0 to 65. And the y's are from 0 to 10. So let's see what happens. Did I remember to put the 1 in? I guess we'll find out in just a minute. Here's this decay curve. It does intersect there. Honestly, I'd like to see a little further. So instead of just going out to 65, I'm going to go ahead and go out to 80. I just picked that number. There's the graph. It's decaying a little bit further. Remember, when the base is less than 1, you get a decay curve. This is the point I'm looking for. So second of the calc, number 5, intersect. And I get that when you are at the depth of, let's see, 60, it's approximately 65 feet. Let's see, round to the nearest whole number. So at what depth? 65. And what point on the graph represents this? Well, the x is 65, that's the depth, and the percent is 1. All right, so now we have a problem that is compound interest again, but this time we're not going to just plug in the principal and the rate and the compounding periods and so on and solve for A. This one, same formula. We're going to complete the table. We want to know time. All right, let's use our graphers to do this. So we have A is equal to, I'll write down the formula and then we'll plug in. A is equal to P times 1 plus R over N raised to the n times t power. The future value, the accumulated amount, is $22,000. The investment, the principal, the present value, is $11,500. And open parentheses, 1 plus, the interest rate is 0.0625, because I had to change this to a decimal, divided by the number of compounding periods is 2, and it is raised to the nt power, so it's 2t. Well, let's just, if we're going to use the grapher to do this, we have to have two unknowns. And so I'm going to let this be y equals. So I'm going to type in y equals 11,500, open parentheses, 1 plus 0.0625 divided by 2, raised to the 2x power, and then I'm going to have a second y equals and say, and the y value is 22,000. If you didn't want to do that and you wanted to do it algebraically, you certainly could. You would end up taking the log of both sides. It would be a little bit on the nasty side. So let's see what we've got. Y equals Alright, so it is 11,500, open parentheses, 1 plus 0.0625 divided by 2 raised to the 2x power. Alright, that's my function. And then I want to know for what x value, which is time, will I get $22,000. Now the hard part here is going to be my window. My time is my x. I don't know if I'm going to go out to 80 years. I really don't think I will. I think I'll go -10 to, I'm going to start out with 10. Now the y's, it's the money. So let's go -10. That's only so I can see the axis, and we'll go up to 25,000. This side over here is not even relevant. Alright, not a very good window. Almost. Over here, I don't need -10. I'm just going to do -1. But I need to go further out. I'll go to 20. Get a slightly different view. There it is. I want to find the coordinates of this point. This is $22,000. Along here is time. So I will do second, calc, number 5, enter, 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 and let's see, round to 1 decimal place is what it says. So this will be x, which is time, will be 10.5 years. Double check that. Yes, 10.5. Okay, so we have practiced a little bit more with our calculator, and we have solved both exponential and log equations, and now it's time for you to work. Good luck.